Let's take a quick look at this comparison table. We're comparing the decimal, octal, hex, and binary number systems. Shown decimal counted from 0 through 7, and then onwards from 8 to 15. You remember that the octal numbers 0 through 7 and the hex numbers 0 through 7 match up nicely with the decimal numbers 0 through 7. It's only afterwards that it gets a little hairier. What we saw when we had a look at binary is that using just 3 binary place values, and binary place values are called bits, so using 3 bits, we can count decimal numbers 0 through 7. In other words, octal numbers, all of them, from 0 through 7. So we can represent each of the 8 octal numbers using 3 binary bits. To do that, we want to think of each binary number as having 3 bits, so I'm going to pad the left-hand side of these numbers with zeros. So now we have a nice comparison for each octal number. We have a grouping that represents the equivalent number in binary. If we extend our binary number to 4 bits, to 4 place values, we can continue counting all of the hex values. Using 4 bits, I can count from hex 0 to hex F. That gives us a nice comparison as long as I include 4 digits by padding the left-hand side of each binary number. I can take each hex number and replace it with a 4-bit binary value. Let's see where we might use this. Since octal is a power of 2, specifically since 2 to the power of 3 is equal to 8, we can convert binary to octal by grouping our binary number in groups of 3, in groups of 3 place values or groups of 3 bits. Let me write down our binary number, 1, 1, 0, 0, 0, 1, 1. How do I do my grouping? I'm going to start at the octal point, in this case on the right-hand side of the number, and group 3 bits at a time, moving from right to left. If I don't have enough digits for 3 bits, I'm going to pad the number on the left, in this case by adding 2 zeros to form a final triplet. Adding zeros to the left-hand side of any number does not change the value of that number. It just clearly indicates that the 1 seen here is in the 1's place value. So now I have 3 numbers. I'm looking at the numbers 001, 100, and 011. So now I'm going to take each grouping of 3 binary place values of 3 bits and convert them to their corresponding octal value. One way to do this is to flip back to my comparison chart. I've got, for example, the binary value 001, and I see that this corresponds to the octal value of 1. I also have the binary value 100, and this corresponds to the octal value of 4. And the final triplet is 011, which corresponds to the octal value of 3. So one way to do this is simply to look at my comparison table. 001 corresponds to the octal value 1, 100 to the octal value 4, and 011 to the octal value of 3. The other way to do this is to analyze each triplet by reading the digit in its appropriate place value, looking at only 3 bits at a time. So this means that the one that I've highlighted here, well, I read this to be in the 1's place value. The 1 to its left, we understand to be in the 2's place value, and the 0 is in the 4's place value. That means that this first triplet is 0 times 2 to the power of 2, or 0 times 4 is 0, plus 1 times 2 to the power of 1, or 1 times 2 is 2, and then 1 times 2 to the power of 0 is just 1. And 0 plus 2 plus 1 gives us 3. That tells me that this binary triplet 0, 1, 1 has the octal equivalent of 3. Right? Whether we're translating into octal or into decimal doesn't matter because the numbers match up from 0 to 7. And since we're using triplets, the largest octal number we'll reach is 7. So you can finish the analysis for the next two triplets in the same way. And we see that we come to the same conclusion as we did using our comparison table. Again, since these numbers are all in octal, putting them together in order gives me the octal value 1, 4, 3. To convert a value from octal to binary, we use exactly the same process in reverse. You'll start with each digit, 1, 4, or 3 of the octal number, convert it to its 3-digit, 3-bit binary number, and write out the final number in order. Let's try one more, this time converting a binary number that contains a binary point. Starting at the radix point and moving to the left, I'm going to group the values in exactly the same way. So 0, 0, 0, and then 1. I'm just reading the binary numbers starting at the binary point and moving to the left. I'm going to pad the left-hand side again with 2 zeros to ensure I have groupings of 3. So I have 2 groupings of 3 to the left-hand side of the radix point. 0, 0, 1 corresponds to the octal value 1, and 0, 0, 0 corresponds to the octal value of 0. Again, starting at the radix point, I'm now going to make groupings of 3, moving to the right. 1, 0, 1 is my first triplet, and then I'm left with a 1. My first triplet is complete, but my second triplet has only one value, so I'll again pad this number, this time to the right. Adding zeros to the end of a number, when those values are to the right of the radix point, does not change the value of the number. But it does ensure that I locate the place value of this digit. This 1 is in the 2 to the power of 2, or 4's place value. Either by translating each triplet into its octal number using the comparison table, or by reading it in its place value, I find that 1, 0, 1 corresponds to the octal value 5, and 1, 0, 0 corresponds to the octal value 4. Putting that together and making sure I put the radix point in the correct position tells me that the octal equivalent of our binary number is 10.54. And I'll be very clear that that's in base 8. Now to convert to hexadecimal, I simply need to take my binary number and group the digits in groups of 4. In other words, I'm going to make groupings of 4 bits. Again, I'm going to situate the radix point, and this number, again, I'm going to start by writing it from right to left. So I have 1, 1, 0, 0, 0, 1, 1. Because I'm now translating to hexadecimal, I'm going to create groups of 4 rather than groups of 3. So starting at the radix point and moving to the left, this gives me 2 groups of 4. That second group of 4 was incomplete, so I'm going to pad the number with zeros. Again, adding zeros on the left does not change the value of the number, it just situates each digit in its appropriate place value. Again, I can return to my comparison table, and I see that the binary quartet 0, 1, 1, 0 corresponds to the hex value of 6. And again, that 0, 0, 1, 1 corresponds to the hex value of 3. Or I can read each digit in its corresponding place value to evaluate each quartet. This first one on the right-hand side, the first digit, is in the 1's place. The 1 to its left is in the 2 to the power of 1 or the 2's place. The first 0 finds itself in the 4's place, and the final 0 finds itself in the 8's place. 0 times 8 is 0, 0 times 4 is 0, 1 times 2 is 2, and 1 times 1 is just 1. 0 plus 0 plus 2 plus 1 is 3. So the binary number 0011 corresponds to the hexadecimal number 3. Let's do the same thing with the second quartet. And we see that the second quartet does in fact correspond to the hexadecimal number 6. Putting those two together, I can see that our binary value is equivalent to 63 in hexadecimal. And finally, let's try a hexadecimal number that also has a radix point. I'm going to write the number carefully, starting at the radix point and moving to the left, 0, 0, 0, 1. So we have a single grouping of 4 to the left of the radix point, and then starting at the radix point and moving to the right gives me 1, 0, 1, 1. I don't have to pad the number on the left or on the right. Reading this value or taking a look at the comparison table tells me that to the left of the radix point, I have the number 8, and to the right of the radix point, I'll come up either with 11 in decimal, or, of course, in hexadecimal, 11 corresponds to the symbol B. So I have an 8 and a B. Putting those together gives me 8 point B in hexadecimal.